here at this point. We could expand this, right? We could multiply all this out, and then we could multiply this all out. We could collect like terms and get an answer, right? We're not going to do that because that is the derivative, and I like it that way. It's nice and clean, all right?
Later on, would we have to?
We will at some point have to do something with this derivative, and so the algebra will come back into play because we're actually going to figure out, we're going to take these derivatives, and the biggest thing we're going to want to do with them is figure out when they're equal to 0. So we'll be solving equations involving these derivatives later. But right now we just want to make sure we get the mechanics down. All right. Yes? Okay. How about this? How about f of x equals sine x times cosecant x? Now, I've called this function f, right? I've called this function f, and do y'all see it's a product of two things? Yes? So it's a product of two things. So if I want to follow my formula over there, I need to call one of them f and one of them g, right? So I'm going to call this f and g, even though the whole thing together is actually f, isn't it? So I guess what I'm showing you is that there's some limitations to our notation, right? If our formula has f and g, then if this is f and it's a product, we're going to have some, we're going to be calling f two different things. So as long as you can get past that and just apply the formula, we should be okay. So the derivative here would be, okay, the derivative, I need to take derivative of the first one, right? Times what? Cosecant x, then plus, now the derivative of the cosecant, right, which I'm going to do is put a prime, and then times the first function's sine. Right? Isn't that the product rule? Yes? Now, what is the derivative of sine? Cosine. So this is cosine x times cosecant x plus, now what's the derivative of cosecant x? Negative, what did you say? Negative cosecant x what? Times cotangent x? Crap. Okay, so you got that off the formula sheet, right? The derivative of that is this. And then we still have next to that what? Sine x. And that would be a raw derivative, wouldn't it? That would be a raw derivative. And on an exam, I would take that as an answer, okay? But I want you to see some algebra here, all right? Because I did this problem on purpose to see if anyone would notice what the original function f actually is. It's 1. Look, what is sine x? Well, sine x is sine x. What's cosecant x? 1 over sine. So isn't this really just sine x times 1 over sine x? And isn't that just 1? And what should the derivative of 1 be? 0. So this answer should actually be 0. But do you see we don't see that? So let's do some algebra and convince ourselves that this is actually 0. This is cosine x times, I'm just going to leave it as cosecant x. Then I'm going to change this to a minus. I'm going to put cosecant x, and because I kind of know where we're going here, what is the definition of cotangent? It's what trig function over what trig function? Cosine over sine, right? So I could write this as cosine x over sine x, and I still have over here sine x, don't I? And do you see what happens to the sines? They cancel. And so what we have is cosine x times cosecant x minus what? The same thing. So your answer is 0, right? So I guess there's kind of a couple of morals to the story here. First of all, yes, there's the product rule. You can get a raw derivative, but cleaning it up can actually be worth it because sometimes that cleans up to be something nice, especially if your original function was just a complicated way of writing the number 1, all right? All right, let's do another one. There's really nothing more to the product and product rule here. Yeah, let's do that. I like that. Square root of x times tangent x, right? That's what's happening. There's multiplication there. Everyone see the multiplication? Is that multiplication between the tan and the x? No, that's composition, right? That is, the x is being plugged into the tangent. So we have our product. We recognize our product. Let's call this f, let's call that g, and let's apply the formula. Go ahead, take a minute. Do it yourself. See if you can get the raw derivative, just the raw answer. Yes? You got it? Okay, hang tight. Is that what y'all have for the first step? Right? If you're writing everything down, derivative first one times second. Hey, listen to what I say here, because you'll hear me say this a lot. Instead of saying the formula f prime g plus g prime f, you'll hear me a lot in the class say this, that the product rule is always just the derivative of the first one times the second one plus the derivative of the second one times the first one, right? And then I'm not even thinking about f and g. It's just which one comes first, which one comes second. Derivative of the first times the second plus derivative of the second times the first. I'm going to say it a third time. Derivative of the first times the second plus the derivative of the second times the first. All right, what is the derivative of this? 1 over 2 root x. That's the way I asked you to try and memorize it, right? 1 over 2 root x and then tan x. And then we need to know what the derivative of tangent of x is. Secant squared x times root x. I cannot put these x's together because that x is trapped inside that secant. So we like to usually put it out front. Also, these, I can rewrite those as a fraction like this. Tan x over 2 root x. Just slide that tangent on top with the 1. Then over here, like I said, change the order. There we go. That's our raw derivative. Algebraically, what could you do with that? I mean, maybe put them together, get a common denominator, but we will do more algebra with these as we progress through the class. For now, let's just focus on getting the derivative done. Questions? I wonder if you have a product, right? What about if you had a triple product? Like what if you had f times g times h and you wanted to take derivative of that? I wonder if there's a formula for that. What do you think? Probably, right? Probably. But you're not going to find it on your formula sheet. It's not there, okay? Because if there was, then we would need one if we had 4 things multiplied together, and then 5 things, right? And then 6 things, and 7. It would become a disaster. You only ever need, for all of calculus, you only ever need this one, all right? Let me show you how we can do this, all right? So what I'm going to do in order to show you that we could come up with a formula is to just look at it this way. Let's put this g and this h together as one group. All right? So if I do that, do you agree I have a function times a function? Yes? Function times a function. And I'm trying to take the derivative. So the derivative of that should be, remember I said it 3 times in a row? I'm going to do the derivative of the first one. So I'm going to do derivative of that one, right? F prime times the second one, but I'm not going to touch that one, right? So the second one is GH. Yes? I could do a parenthesis or bracket if I wanted to. I don't have to because it's all multiplication. So that's derivative of the first one times the second, right? Plus, now what? The derivative of the second one. So that means I have to take the g times h, and I need to take its derivative, don't I? Then times the first one. Do you all see that that product rule applied to this? Yeah? F prime times g times h plus g times h, take the derivative times f. What do we still need to do then? The derivative of that. But isn't that a product rule again? So this is going to be f prime times g times h plus, how do you do that? How do you do this? The derivative of the first one, which is g prime times the second one, h, plus the derivative of the second one, h prime times g, right? But that's just that piece in red. What do I still have attached to the end of this? Times f. And then what I could do is I could say, okay, this is f prime times g times h. I could distribute this f through, make it g prime times f times h, and then distribute the f through here plus h prime times f times g. And that would actually be a formula. What's important here is not that you memorize the formula, okay, at all. In fact, I don't have that written down anywhere. You're not going to see it anywhere. What's important is that you see that in order to do 3 things multiplied, we had to do a product rule, and then within that product rule, we had to do another product rule, right? So I think it's better for us to actually do an example where I give you 3 functions, and we actually go through this and not use the formula. So
Is it because you distribute the f?
this right here, and this is the f getting distributed through this like this. To show you that we can do it. Right? If we have 3 things being multiplied, there is a way to take a derivative. Right? No? You don't seem happy? You're not happy? It's okay. You can say you're not happy. This is a problem out of your textbook, so I wanted to at least address it, like it's in the book. So let me show you a specific example with specific values of f, g, and h. It's like 3 different functions. So what if I wanted to do, let's say our original function was f of x equals, I'm running out of good markers here. Let's do x squared times sine x times x cubed plus 1. I want to know the derivative of this. You'll see how we have 3 things being multiplied? Right? We have 3 things being multiplied. So what I'm going to do is I'm going to clump 2 of them together. And that's up to me how I do that. So let's put these 2 together into one and see that I have multiplication. So I have a first function and then a second function. You all see them? So let's now use our product rule. The derivative of this should be the derivative of the first one times the second one. Now the second one is everything we see here in this bracket. That makes sense? Yes? We have something times something, the derivative of the first one times the second.
It's x to the third.
X to the, yeah, thank you, x to the third. And then plus, now I have to take that sine x times the x cubed plus 1, that right there, I need to take it and take its derivative and then times the first function, or yeah, times the first one. So I have a first function and a second function. The derivative of that is the derivative of the first one times the second one plus the derivative of the second one times the first one. That is our product rule to start. Do you know how to take derivative of this?
Yes.
Yeah, it's just what? 2x. Okay, so this becomes 2x, and then I have this still, right? Now, I actually don't need the brackets because there's no additions in there. Those are all being multiplied together. It's this derivative times that times that. So that's this first part. Plus. Now what do we have to do? A product rule of this, right? That requires a product rule because there's a product right there. So to take the derivative of that product, I have to apply a new product rule, which will be the derivative of the first one times the second, plus the derivative of the second times the first. But we can't lose sight of the fact that whatever the derivative of this is, we still have an x squared tacked on to the end. So whatever my answer is in here, whatever that derivative is here, remember it's going to have an x squared multiplied in at the end. So let's go and do our product rule right here. Derivative of the first one, cosine x times the second, plus derivative of the second one. So what's the derivative of x cubed plus 1? 3x squared, and that's it, right? Then times the first one, which was sine x. So I actually didn't show it, I just did it. Derivative of that is this, times that, plus the derivative of that is this, times that. But all of this times x squared. Can you all imagine how you could actually extend this out to 4 things being multiplied? It would suck, but you could do it, right? If you had 4 things, you could group them into like, 2 and 2 if you wanted, or you could go one of them with 3 of them. I wouldn't give you anything like that on a quiz or test. This is just to go to show you that we actually do have a way of doing more than just 2 things being multiplied. All right, so what could we do now? I mean, this we could just leave alone. We could distribute the x squared through here, right? Here to here to here if we wanted to. But that's our raw derivative, so let's just leave it at that. All right?
So that was my question on the last one. Like,
Yeah.
what was the point of distributing x? Well, just because you could.
Distributing that f at the end? Was it an f?
Yeah, but
You didn't need to.
Oh, okay.
No, you didn't have to. How do we know when we're done? When you have no more primes, okay? When you have no more derivatives to take. Once you've taken all the derivatives, you're done with calculus. And now you're back in algebra. All right. How about this? What if I give you a function
can you do x to the third plus x plus 1 times and x to the negative 1/2 plus.
Are you trying to bring this up or something? Okay. You could try and bring this up, okay? You could try and bring it up, but I promise you it's going to be worse if you try and bring it up right now. Assuming the only rules we have are power rule and product rule. If those are the only rules, easiest thing to do, well, we're stuck then pretty much. Were you going to say something? Yeah.
Yeah, isn't it the low D high times high?
Yeah, so this is a quotient, right? Not a product. We can look at this as a quotient. And so it becomes natural to ask the question, do we have a rule for the quotient, right? Do we have a rule for a quotient? Well, we do, all right? We do have a rule for the quotient. Now, I'm not going to go through the proof, all right? I did the proof for the product. Is that good enough? Can I give you just the rule for the quotient? And yes? All right. So for the quotient, let's take a pause here, okay? I'm going to say, I don't know how to do this, because all I know how to do is take derivatives of x to powers, and if I have a product, I have a product rule, but I don't have a quotient rule yet. So let's go to our formula sheets. It's probably formula 6 on reference page 5. Let's see what the book has here. Reference page 5, yeah, formula 6. And what I'm going to do is I'd like to write down the book's version of both of these again. So formula 5 was the product rule. The way the book had it written is something like this. If you try and take derivative of that, they're telling you to do f times g prime, then plus g times f prime. That was is it all right if I use that notation without the x's, f of x, g of x? Isn't that the book's version? If you have f times g, you want to take derivative, you do f, then times g prime, and then plus g, then times f prime. Right, that's the book. And then for the quotient, formula 6, they say this. If you take the derivative of a quotient, I need to start throwing these away. I keep moving these like on different parts of the board, and then I keep going back to them, so heads up. Ah, close. All right, so according to the book, what's the answer to this? To the formula sheets. G times the derivative of f, right? So g times the derivative of f, then what? Minus f times the derivative of g, and then over g without a derivative, just square it. So that is actually true, that is correct, okay? That is correct. According to the book, this is your product rule and this is your quotient rule. I said I like this version for the product, right? So can I write mine underneath these? Okay, so this is the book. In black, I'll do mine. What I said for me is I like f, the product rule to be f prime g plus g prime f, right? That's my version, book's version. Now, you ready to see my version of this? My version of this is f over g, take the derivative. What I do, that's the book's formula. All I do is flip those two around. Okay, what would happen if I flip those two around? F prime times g, then minus, I'm going to flip those around, g prime times f, and then all of that over g squared. That's my formula that I like to use. Anyone want to look at those versions and maybe take a guess as to why I like the way I do it as opposed to the books? Do you see? Quotients are always what? Not sure. Yes?
The only thing that changes from the two formulas is the quotient one has g squared.
Yeah, look at the way I do it, and I'm not trying to say I'm like any better for this, but when I was a student, I learned it this way in blue. And then as I started to understand things better, I was like, why can't we just do it this way in black? Look, what's the difference between this formula and this formula if you look at my version? Is there any difference between this and what's up here? Just subtraction, right? There's one difference. Plus here, minus here. That's not a huge difference, is it? So just remembering that when you're doing a quotient, that plus becomes a minus, and then you have to divide by g squared, right? So these formulas are very similar to one another, aren't they? Whereas if you go off of the book, like I said, when I was a student, to me, these are completely distinct formulas. Like this one is f, then g prime, then plus g, then f prime. But over here, it's g, then f prime, then minus, then the f, then the g prime, then over g. They seem too different to me. As a student, they seem too different. It's like I really have to think about each formula separately. Where here, as long as I get this down, the quotient rule is the same thing with the minus and then divide by g squared. All right? So you're free to change it on your formula sheet if you want, or you can stick with the book. If you go to a tutor, You go to a friend that took calculus already, I would be willing to bet you money they're going to give you one of these two versions because that's the way they learned it. Okay? But that's not the way I'm going to teach it. All right? I don't care what you use. Get it right. That's all I'd say. All right? Just get it right. So you ready to do this problem? I'm going to put my version over here. I only say my version because I've never seen it this way in any book. So no, thank you. Doesn't sound fun to me. Textbooks are, well, now it's all ebooks, right? I mean, it's. All right, here we go. So what we're going to do on this is we're going to have to, if we see a quotient, we have to like pick, you know, the top and the bottom. It's like the top is the F and the bottom is the G, right? And we're dividing. So how do you do that? Well, according to the formula, the derivative of that will be what? The derivative, instead of the first one, you know how in product rule I was saying derivative of the first times the second plus derivative second times the first? That's what I said with the product. Here, we're talking about top and bottom. So it's going to be derivative of the top, right? What's the derivative of the top? Well, whatever it is, right? It's going to be x cubed plus x plus 1 derivative, right? That's the derivative of the top, times the bottom, which is x plus sine x, and then minus, now I take the derivative of the bottom, and then times the top, don't take the derivative, and then all of that over the bottom g, but squared. So you take the entire x plus sine x, and you square it. There you go? Yeah. All right.
300.
What now? Can you do those derivatives? Can you? Derivative of that is 3x squared plus 1, right? Oh, that's way off. I'll get those. I'll get them. I don't want anyone to hurt themselves. Ooh, good one here. X plus sine x minus, right? Now I take derivative of that one, right? I'm going to have two terms there, right? Derivative of x is 1, and then plus derivative of sine is cosine. And then we still have to multiply that times this one. Don't take the derivative. And on the bottom, do you think we should actually square that? No, let's not do that. That's too much like work. All right? So there we go. That is our raw derivative. We've taken derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. Say it again. Derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. Now I know some of you have learned this before and you were taught this thing, this cute little thing to help you remember how to do this? It's low D high minus high D low. Anyone else? Yeah. Yes, is that how it goes? Yeah. Low D high. So I think the way they're doing it is they're using the Book's formula for that. Right? Because the Book's formula was G times F prime minus, what was it? Low D high, high D low, right? So the way this thing goes, it's like a cute little saying, low D high minus high D low, all over low squared. How many of you have heard that before? Okay, only 1, 2, okay. It's cute. If you want to do that, that's fine. However, it only works for the Book's formula because it's, when you look at the F over G, low is the bottom one, high is the top one. So low D high, low derivative of the high. Low D high minus high, the top one is the high one, D low, derivative of the low one. Low D high minus high D low, all over low squared. It's cute, but I don't like cute things. So, I mean, I just don't. No, it's kind of like FOIL, right? Isn't FOIL cool? Like FOIL's, we all learn FOIL? But it doesn't work if you have more than, if you have 2 times, binomial, you want to FOIL, great, but what happens if you have 3 and 3? You don't have FOIL anymore, right? So what is it called when you multiply something like that out? Expansion. It's called expanding, right? Distribution. So I like cute things, but, to me, the cuteness of low D high minus high D low is offset by the fact that this formula looks completely different than the product rule formula. I like the similarity of these 2 formulas. Again, if you've learned this stuff before, you've seen these formulas, I'm not here to try and sell you on my way, but if you've never seen them, then this is the way I'm presenting it, right? What more do we need to do? Like calculus-wise, are we done? Calculus-wise. Yes, right? We've taken the derivatives, we're done. The rest would be algebra, right? And there's a lot of things we could try and multiply these things. We could FOIL these, right? We could FOIL those. We could FOIL. No, we can't FOIL that. We can expand that though, right? So we could do that, but there's no need to, right? The question was to find the derivative. Did we find it? Yes, we're done, all right? How we doing? Y'all hanging there? You took a test. I commend y'all for hanging in here. I really thought there would be like, half of you would finish the test and walk out and not stay. I feel like there should be a reward or something. Maybe we'll do a little reward here at the end. All right, I have another one for you. I'm not sure if y'all are ready for me to turn the screws too much here, but let's see. I told you that we're going to get these rules and do away with the limit, right? So we're going to get these rules, and it's going to be great. We don't have to do limit anymore. And I said, but the give and take here is that now we're going to have to be able to find derivatives of more complicated functions. This one's a little bit more complicated. Because when you look at it, ultimately, do you all see you have a quotient? So you're going to have to do the quotient rule, which is going to be the derivative of the top, right, times the bottom, minus the derivative of the bottom times the top, all over the bottom squared, right? That's what we're going to do. But when we do the derivative of the top, what do we see the top is? It's multiplication. So when we do that derivative, we will have to apply the product rule, right? So let's just take our time, write everything down. Let's not miss anything. The derivative of this will be, using our quotient rule formula, the derivative of the top. So it's whatever the top is, take its derivative, times the bottom, minus, then I have to take derivative of the bottom,